TensorFlow is another popular ML library supported by ROCm. It was originally developed by Google to accelerate model development. Like PyTorch, TensorFlow provides programmers with high-level APIs for building and deploying end-to-end ML models. ROCm offers support for TensorFlow through pre-configured Docker containers, which simplify applications development and deployment. Under the hood, TensorFlow leverages ROCm libraries such as MIOpen and ROCblast along with heap calls to deliver high-performance ML capabilities. This allows unmodified TensorFlow code to seamlessly execute on AMD GPUs enabled with ROCm. To begin working with TensorFlow on ROCm, our initial step involves installing TensorFlow by pulling the respective Docker image. Similar to PyTorch, we can pull the TensorFlow Docker image for ROCm by executing the command docker pull ROCm/TensorFlow:\latest. After pulling the image, we can run the container using the command from the slide. This command launches the container with the specified configurations, allowing you to interact with the TensorFlow environment provided by the ROCm Docker image. Now that we have gone through the installation process, it's important to ensure that TensorFlow is installed correctly and functioning properly. We can do this by importing the TensorFlow package in Python. Running this simple command from the slide will help verify if TensorFlow is properly installed. If it is, we will see a success output indicating that TensorFlow is ready to be used. Otherwise, we will see a failure output indicating that further troubleshooting might be needed. With TensorFlow successfully installed, we can proceed to run a basic TensorFlow example within a Docker container by executing the command from the slide in the terminal. This command enables us to run the Docker container in interactive mode and execute a Python file. When we run this command, we enter an interactive mode within the Docker container where we can execute commands, run Python scripts, and access files within the container. The mounted directory located at the host machine becomes seamlessly available as the root directory inside the container. This seamless integration allows for easy file sharing and execution between the host and the container. Now let's run a Python code for TensorFlow and observe the utilization of the GPU or CPU. The code from the slide is testing whether a GPU is available for training the model or if the training needs to be done on the CPU. The code first loads the Cipher10 dataset and preprocesses the image. Then it defines a sequential model with a flattening layer, a dense layer with ReLU activation, and a dense output layer with softmax activation. Next, it compiles the model using the Adam optimizer, sparse categorical cross-entropy loss, and accuracy as the metric. The if statement checks if a GPU is available using the tf.test.is_GPU_available function. If a GPU is available, it prints training on GPU and uses the GPU device to feed the model to the training data for 10 epochs, with validation data provided. If a GPU is not available, it prints training on CPU and feeds the model on the CPU. Finally, it evaluates the model on the test data and prints the test accuracy. The screenshot on the slide shows the use of the GPU for processing the model's output during the execution of the Python code. The presence of the print statement in the code, which states training on GPU, specifically ensures that it is only displayed when the GPU is being accessed and available. Afterwards, the model is evaluated on the test data, resulting in a test accuracy of 0.4213 approximately. This serves as a simple illustration highlighting the utilization of the GPU in a basic model. However, it may not exhibit optimal efficiency. Feel free to explore more intricate models and incorporate TensorFlow on ROCm to further enhance performance.